So hi everyone, and welcome to everybody to another session of this most seminars online series. Most are presentations from leading young academics in mathematics from around the globe, and the idea is that the talks being presented here are accessible to a broad audience, no matter the field in mathematics that you are. The idea was to inspire the new generation of young mathematicians, so those who are working towards or have just completed a PhD in mathematics. It is online, as we can see, but shortly after each talk, we will upload it into the European Mathematical Society YouTube channel. Talks are 45 minutes long, and then we have 15 minutes for questions. So today we have Adam, and I'll let Jelena present him.
Thank you. In 2008, Adam began his study at the Nicolaus Copernicus University in Torun. He graduated in 2012. In the same year, he enrolled PhD studies in the Institute of Mathematics, Polish Academy of Sciences, under the supervision of Professor Marius Lemancic, and he obtained a Doctor of Science degree in 2015 with thesis title Ergodic Properties of Smooth Flows on Surfaces. From 2015 to 2018, he worked as research assistant professor in the Penn State University State College. After that, he became assistant professor at the University of Maryland. In 2021, he got a position as associate professor at the University of Maryland, where he was promoted to full professor in 2024. Area of his scientific interest is vast, and it includes dynamical systems and ergodic theory, as well as their interaction with number theory, geometry, and probability theory. Adam has published more than 35 papers in prestigious mathematical journals. He has received many awards, but I would highlight three from last year. The Simons Foundation named him a Simons Fellow in Mathematics. He received the prize of Institute of Mathematics of the Polish Academy of Sciences for outstanding scientific achievements in mathematics, and in the same year he was awarded the EMS prize for his outstanding contributions to the spectral classification and the mixing properties of slowly chaotic dynamical systems. I would also like to mention that Adam has two daughters, and in June 2024, he completed his first Ironman triathlon, which is quite impressive. Now I give a word to Adam. You can start sharing your screen. And also, I would like to mention that if you have some questions, you can ask Adam during the lecture or after the lecture.
Yeah, so let me try to share the screen. And yeah, if there are any questions, please feel free to interrupt at any point, and I will try to, if I can, I'll try to answer, or yeah, just admit that I can't. I can't see, so one of the features here, at least as to my abilities of using computers, is that I can't see anything except my presentation if I'm in full screen. So yeah, if you have a question, maybe you speak up or something. I mean, I won't be able to follow the dynamics of the meeting.
Yeah, don't worry, Adam.
We will tell you.
All right. Yeah, so thanks for inviting me. It's a great pleasure to give a talk to this audience. Yeah, so I've chosen a part of what I'm interested in, and this part is somehow on the intersection of ergodic theory and dynamical systems and number theory. So not so much to today's talk is not going to be so much on say applications to geometry or probability. It's rather number theory and dynamics, I think. Yeah, so let me maybe introduce you first what we study in dynamical systems. So generally, dynamical systems are concerned with evolution of a given system under time, and the motivation comes from applications. But the general mathematical setting, is usually the following. So we have a topological dynamical system, which means we have a metric space and a map of the metric space that is, say, invertible. Quite often you can talk about, manifolds and smooth maps. So there are various settings, but maybe this is the one that, say, classically one would use. And then on this space, on this metric space, you have the set of probability measures. So, you want to measure somehow statistics. So probability measure is a measure on the space that such that the measure of the space equals 1. So finite measure, and in fact you normalize to be 1. Then the fact that you have a metric space gives you a natural class of sets, which are open sets or closed sets, and then you make a sigma algebra of it. So far, these two don't have dynamics. The third point sees the dynamics, or so the T, the evolution of the system, and measures that are convenient to work with in terms they describe the statistical behavior of T are so-called invariant measures. So a measure is invariant if I take a set and I push it by my dynamics, either forward or backward. In the invertible case, it makes no difference. And the measure doesn't change, right? So obviously, the set of T invariant measures which we have is a subset of all probability measures, and is denoted by mxt. And here comes the first theorem that actually we are going to see a proof of. So one of the basic things you learn when you take a course in dynamics, say in dynamical systems, is that the set of invariant measures is non-empty. This is a maybe 50-year-old theorem. And the good thing about this theorem is that the proof is, I think, more important than the statement of the theorem, in fact. And we are going to see the full proof. So, because I think, for people maybe not working in dynamics, it really shows what's going on. So, how you build these measures. So, you take any point in space, and you consider what's called empirical measures. So, you just take the orbit of your point. It can be any point. For example, if it's a fixed point, then the measure mu n is just going to be Dirac at the fixed point. But generally, you just take an orbit, you iterate n times, and you put equal masses along the orbit of length n. This gives you a sequence of measures mu n. And these are probability measures because you've put masses 1 over n. So they sum up to 1. Okay, they are not invariant, not T invariant. But there are two facts that somehow make it work asymptotically. First, there is an abstract argument that the space of probability measure is weak star compact, so you can take a limit point of mu n. Your favorite one. The abstract, weak compactness guarantees that such a limit point exists. And then the measure that you obtain as a limit is invariant, in fact. And the reason for this is that if you take the set, say, from 0 to n minus 1, right, and you shift it by 1, which means you take the orbit from 0 to n minus 1 and you push it by t, now you have an orbit from 1 to n, right? But notice that not much changes. It's just the first instance and the last instance that are different. The rest is just the same. And hence the limiting object will be invariant. So that's a nice, I think quite instructive proof. And that's more or less the only way to build measures. So your system might have many invariant measures. Notice here you have two freedoms. You have the freedom to take the point x. You can pick any, and any point is going to give you something. And you are allowed to take different subsequences. So any limit point is going to work. But this sequence of measure might have many limit points, and then you get each one gives you a possibly different measure. Sometimes it happens that you just get 1 point, and then we call the system uniquely ergodic. So this is, as you maybe get the intuition, it's a rather strong assumption because This means that every point and every subsequence I take leads in the end to the same measure. So unless there is some extra structure about the system, no way we can expect this to hold in generality, right? And I just give two examples of dynamical systems. The first one is full shift. So that's a model for just coin tosses. So basically you take sequences of 0, 1s. That's your metric space, X, right? 0, 1 to the Z by infinite sequences. And your transformation T is just taking the sequence and shifting it by 1. And that's called a full shift. And it turns out, we are not going to prove this, that the set of invariant measures is a huge set, whatever the word huge means. But you know, like you have, at the very least, you have periodic points. So you can take, like, for example, the sequence 0, 0, 1, 0, 0, 1, 0, 0, 1. And this will give you a measure that will be a periodic measure. In fact, any periodic point gives you a periodic measure, a different periodic measure. But there is much, much more than that. The other extreme in dynamics is irrational rotations. So this, you just take the circle and you rotate it by an angle alpha, where the alpha is irrational. And this one is actually uniquely ergodic. So that's a classical result. That irrational rotations only have one invariant measure, and that's the Lebesgue measure, by the way, on the circle. So just the arc length. For people maybe working a little bit in algebra, the second example is a subclass of a more general set of examples. So notice that for irrational rotations R, so the real line is in particular a Lie group, and Z is what's called a lattice in R, meaning that it is a discrete subgroup such that the quotient is compact, right? And you can generalize this. So what I wrote is, I think, a rather obvious generalization. You can take any Lie group, you can take any lattice inside the group, and then you can rotate. The same way as you rotate on the circle, you can rotate on the more, what's called a homogeneous space. Here, of course, if the group is non-abelian, you should expect very different behavior. And yeah, here I'm not mentioning more. It's just that you might get, very different behavior. And this depends on the group G. Somehow, the less abelian the group is, the more randomness and the more measures you can see. But it also depends on the element G, the element you rotate by here. Okay. Yeah. As I said, so ergodic theory and dynamical systems are concerned with evolution of system under time, and the way you observe the evolution is through what's called observables. So I'm going to state now 3 ergodic theorems, classical ergodic theorems. So an observable is just a function f, say that's now you can choose the smoothness you want. The first theorem deals with L2. You take any invariant measure for the system, which you have at least one, and you take any function f in L2, and the statement, this is von Neumann theorem, so 1930s, is that there exists a t-invariant function f star such that the averages converge to f star in L2. So this is an L2 statement, purely L2 statement. So the way to think about this is a kind of a key object, the MNF of X. So these are what's called ergodic averages. So what you do is you take a point X and you just iterate it n times. F is your observable somehow. This measures your statistics. For example, think of a characteristic function of a small ball or so. And then you average and you see, for example, if it's a small ball, you see how often do I go to the ball. And then it turns out that, for example, under extra assumptions, so here this is, a very general theorem. There are no assumptions on on the measure. But under extra assumptions, you get say, if the system is ergodic, you get the correct limit, which is, so how often I visit A is equal to the measure of A, to the proportion that A occupies in my space. This is an L2 statement. A much harder theorem is Birkhoff's theorem, which tells you that the convergence holds for almost every point. Okay? L2 is a good space because it's a Hilbert space. So here, for the proof of von Neumann theorem, you have basically the theory of unitary operators in Hilbert space, and scalar products that work in your favor. Here, the second theorem is you just take a typical point. It's a much harder statement to prove. Still, both of these statements, as you see, so you need to start with a measure, right? So you have a topological system xt, you pick a measure that you like, and then something happens for typical points, where typical means either almost every or in L2. Quite often you're interested what happens if I fix the initial condition, right? So you take the topological system xt, and someone gives you the x. There is no measure involved. And this is a statement that covers every initial condition. So if the system is uniquely ergodic, meaning there's just one statistics, if you remember the proof, just one measure that you asymptotically get, then you have convergence for every point and for every continuous function, okay? And it's uniformly among all the points. So unique ergodicity allows you to access the topological information about your system, where you can pick your favorite initial condition and see its evolution, right? These two are somehow kind of useless if I give you an initial condition, right? Maybe you can build a measure, so you can still do something, but this one, the third one, is a much stronger statement. Okay, so what I want to talk about, so this is all classical, I would say. What we've discussed, I think Birkhoff is maybe 40s, so it's in some sense history. What I would like to discuss and somehow introduce today is what's called non-classical ergodic averages, and this is the part where number theory somehow comes in. So now the twist will come from the fact that we take a bounded sequence AN. Say you can think of real numbers. This is what all we are going to do for today, I think. And then you take similar expressions, except you weigh by the sequence AN, okay? So now it's not necessarily equal weights, but some iterates of your orbit might be more important than others, say, roughly, right? And here are examples. So if AN is just 1, then we are back to classical ergodic theory. This is a first non-trivial example. So if AN equals 1, if n is a prime, so AN detects primes, then we are going to look at expressions of that form. So then Wn, so these averages are going to be 1 over pi n, where pi n is the number of primes, okay, up to n. So you always need to, in dynamics or ergodic theory, we don't worry so much. We sometimes skip talking about the normalization. It always needs to be the right one. So you are summing over primes up to n, certain expressions. So you need to normalize so that in the limit you have chances to get something, and you're summing primes. So the number of primes is the correct normalization. More generally, you can take, so for example, AN equals 1 if n is a product of 2 primes or 3 primes, or at most 3 primes, and so on. Yet another example is what's called polynomial ergodic theorems. So you take, for example, p of x equals x squared, a polynomial, and then for this one, the corresponding averages would be just, again, you're summing over squares, and you need to normalize by the correct thing. A slightly different example is the Mobius function from number theory. So I will define it later, but mu n is basically -1 to k if n is square free and is a product of k different primes and 0 otherwise. And then the averages you get are of that form. So mu n, ft, and x. The 1 over n here comes from the fact that, I'm skipping this, but sum of absolute values of a Mobius function is roughly n. So yeah, it's all correct, even though one needs to say something why I'm normalizing by n. Yeah. And okay, you have these averages. right? And now a natural question that I think initially appeared maybe in the 70s, I think, is what happens to the averages? So, you know, for an equals to 1 or standard averages, we have these 3 theorems, von Neumann theorem in L2, almost everywhere convergence, so Birkhoff theorem, and then everywhere convergence for unique ergodicity. I mean, under the extra assumption, generally it will not hold simply. So what happens for these averages? Yeah, so I would like to discuss basically briefly the L2 and almost every case. This is kind of a brief discussion, just maybe highlight the main developments. And then I'm going to move to every initial condition. So the goal of this talk is, if you want, you take a point X in your dynamical system. You can think of a rotation even, but that's known, but to begin with, you can take a rotation and you look at the orbit along squares, for example, n squared, so x plus n squared alpha. Does this equidistribute on the circle? Do we have a limit and so on? So this is the type of questions we are going to be interested in. I mean, that's the bulk of the talk. But for that, I felt it's for completeness and also for clarity, good to discuss the L2 convergence first. So if you look at the proof of von Neumann theorem, as I said, you know, it's an L2 statement, and L2 is a Hilbert space. So if you have a dynamical system with a measure, then you have what's called the Koopman operator. So it's a unitary operator on L2 where you just take a function and you push it by your dynamics. This is an operator that's unitary, that's easy to check. And it turns out that there is a powerful statement which kind of reduces the L2 dynamics of my system to basically rotations in a sense. So here is the highlight of the spectral theorem, which is also classical but very powerful. So if you give me a function f, then I can find a measure on the circle such that you see this unitary operator when applied n times. And if we hit it against f, it's going to be just z to the n against that measure sigma f. Okay? And then, for example, so, you know, I'm not going to give details here. It's just a flavor of how things work. Having the spectral theorem tells you that if you want to study averages, this W and Fx in L2, it reduces to study of exponential sums. So, for example, if my an was just n squared, so I'm looking at the n squared, and I have any dynamical system xt nu, through the spectral theorem, right, I can look at these correlations in L2 through this z to the n. I mean, with this correspondence, it reduces the problem to studying what's called, well, quadratic exponential sums, right, or quadratic sums, n squared theta. And this is well understood. So basically, I want to say that for all the sequences that I listed there before, you can pick your favorite one, for example, primes, or whatever. The dynamical system you begin with plays no role, almost, because in the end, you're studying exponential sums, right? Of course, the information about your system is encoded into this measure on the circle, right? So, for example, the measure that you get here, it might be a measure supported on rational numbers, and then you have rational exponential sums which behave very different from irrational exponential sums, right? So the work is still not yet done because you need to understand in general what the sigma f is, what's the support, because this is then going to give you the frequencies for the exponential sums you're interested in. But somehow this is the main reduction, and you know, from there it's classical to establish convergence, say in L2 of all these examples AN that we saw previously. Now, almost everywhere is way more difficult. It took many years and some breakthrough work of Bourgain. So he was able to show that for all dimension sequences, squares, primes, and so on, you can get a Birkhoff-Ergodic theorem, I mean the cousin or the corresponding theorem, also for almost every x. Okay, so the limit exists for almost every x. And this is where, whereas L2 convergence is more or less, it reduces to something classical. There is not much there. This is really a deep harmonic analysis approach that I'm not going to go into, but it's still, you know, there are still questions open and there is still work where one develops the approach of Bourgain. So yeah, so you use basically the circle method, I mean the Hardy-Littlewood circle method and harmonic analysis. Yeah, and from now on, so I don't know if there are questions, but from now on I would like to focus on every x in X. So basically for the rest of the talk, so I think like 25 minutes or 23 minutes, I want to focus on the following problem. We take a dynamical system xt, we take a point x, and now we have a sequence, say squares or primes or the Mobius function, and we want to see the behavior of these averages, but where the initial condition is fixed. So you see a priori there is no measure here. Like it's all the theorems on almost everywhere convergence, they obviously need to have a measure because it's almost every. So remember, almost every means with respect to the measure you begin with, right? So yeah, okay. So let me just say this. So if xt is a topological dynamical system and f is a continuous function, say, the question is, does the limit exist for any initial condition x in X? So no measure involved, purely topological statement. And obviously you need to do something because, you know, if you take a full shift and say you study primes or squares, doesn't matter, you can easily build a point in the full shift for which the limit does not exist, right? So even for regular averages, even for an equals to 1, right, it's easy to build a point where the limit does not exist. And basically what you do, so you know your points are by infinite sequences. So for example, if you're interested at a point which does not have a limit at squares, you would take the first 100 squares, 100 positions of x of your point that you're constructing, and put zeros there, for example. And then for the 1000 window, you would put ones, and then for 10,000 you would put zeros again, and so on. And this works for any sequence, literally even integers, right? So and then you see, depending on what the capital N is, you either see if your function f tells you the coordinate of x. So when you start shifting, you're going to see the coordinates. So at some instances of capital N at one sequence and k, say 100 and 10,000, and then further on you're going to see zeros, and then you're going to see ones along a different one. So no chance. But it's not so hard to show that if you have a zero density sequence, that's important here. So like primes or squares. And then there are systems of zero entropy. So here the shift, it's basically the reason it doesn't work is that there are too many points. Zero entropy means that your space doesn't have that many points, but still you can have a uniquely ergodic system, right? That's why I'm assuming here that the supremum of an, the support of an is zero density, because if an equals to 1, then by unique ergodicity, I mean, we can't have a counterexample. But if it's zero density, then you can find a relatively nice low complexity system where you don't have a limit. And this motivates, you know, some additional assumptions you need to make on your system. Yeah, and now I want to go over what's known and what's not known and what the approach is to study these problems for every point. Yeah, so let's start with Mobius and Liouville functions. So I'm going to define them. I don't know if you know the definition or not, but it's a simple definition. You can think about Mobius or Liouville, whatever I say holds for both of them. The only thing that kind of matters here is that they are multiplicative. So you take a function on the integers, and then, I mean, maybe it's easier to read the definition than if I say it. One important thing is that the function is multiplicative. So if you take a product of two numbers that are coprime, the function evaluated at the product is a product of the values. And for example, rather, I mean, maybe not so recent anymore, but still recent conjecture of Peter Sarnak is that you see, if I take the Mobius function, but the same holds for Liouville, then for any system with entropy 0 and for any continuous function, the averages go to 0. Okay, so here I want to point out it's a very strong statement, right? Because basically the right-hand side doesn't even see the function, right? So somehow there is so much randomness in the Mobius function mu that you can't capture it, you can't correlate it with an observable coming from an entropy 0 system. So here the crucial assumption is the one that's highlighted, the entropy is 0. So basically, you know, Mobius is uncorrelated to the entropy 0 case. Yeah, and this I said just that 0 entropy plays the role of unique ergodicity for this. Yeah, so remember, this is what we are after. The conjecture is still open in full generality, but there have been many systems. So, you know, the conjecture talks about all systems of entropy 0, but you can, there are many dynamical systems that people study. And you can ask what happens for this particular system, right? And there are many such systems for which the disjointness was proved. And the main tools in studying those are, I would say, number theory tools. And here the main breakthrough is now already 10 years, is a result by Matomaki and Radziwiłł, which says that the Mobius function oscillates. So what you should think of is that Mobius function takes randomly values -1 and 1. So here this theorem tells you that if you take a short window, so x is the long window, and you take a short window within of size h, and h can be like log x, and I mean very short. Then on most of such windows, so this is the most x, the Mobius function exhibits cancellation. So you can't have a block of 1, 1, 1, 1. There's gonna be about h over 2 half ones and half negative ones. So that's kind of the number theory input behind the success, partial success of this conjecture for some dynamical system, some dynamical systems. Yeah, there are also some developments by Tao, with the addition of Tao, Teravainen, and Ziegler. And then there is the dynamical feature or dynamical approach. Usually you obtain good results when you combine them. So there is the number theory, and this is the dynamical approach, which is type 2 sums. And this has to do with a very general criterion. So you take a bounded sequence, any bounded sequence, and if you want to see it does not correlate with Mobius, so look at the last line, mu n xn is small o of n, then what you need to do is you need to study what's called bilinear or type 2 sums. So xpn, xqn. Which in dynamics reduces to studying these expressions, okay? And these were kind of they have a well-built theory, these expressions, and this is related to joinings which were introduced by Furstenberg. So these are TP, so notice that this is just a regular, so you started with an average with a Mobius, but you end up with a regular ergodic average for a more complicated transformation. So somehow the trade-off is I can take the weights to be 1, but I need to complicate my transformation. It's not t anymore, it's a product of the power of p, t to power p and t to power q. But still it's a question in classical ergodic theory. So remember, classical ergodic theories, there are many tools, and this is where we want to reduce our problem, and this is one such reduction. The important feature here is that there are no rates. So you don't need, you see the criterion, it has no rates. It's just small o of n for the type 2 sums, which gives you convergence, which is rarely the case. Yeah, so this is for the Mobius function. Now maybe let's discuss shortly the primes. Yeah, so a number is called a k prime if it's a product of k primes. They might be the same. So P1 might be equal to P2, for example. Yeah, so here the expression you're interested in is well, just counting, you divide by the number of primes and you look at the prime orbit. And this is a different, very different question than the Mobius orthogonality because primes are not multiplicative. And usually you want the entropy to be 0, otherwise you can build silly counterexamples. So you want to assume that. Yeah, and there are some standard results. So let's talk about the prime number theorem. So if X is just a point, then this is just the standard prime number theorem from, the one from number theory. If X is finite, then it's a prime number theorem in arithmetic progressions, also classical. If X is a circle, then this is due to Vinogradov. So he showed that the prime orbit for an irrational rotation is equidistributed. So P alpha is dense, but also equidistributed on the circle. And there are some more results. Maybe I'll skip them that you can look at. Yeah, I maybe don't want to say too much about them because in the interest of time, I mean, maybe you can try to read if you know what the objects are. Then these are essentially a complete list of results. It's much less is known than for the Mobius orthogonality problem, and the reason is the reason is in the method, and the method is essentially up to very recent. There was just one, which is called the method of type 1 and type 2 sums. And it's classical. It's already due to Vinogradov. And this is, okay, so this is, you always need to have a slide that's scary. So this is, I don't know, yeah, it looks maybe scary, but it's not. So it's probably best to read it backwards. So the statement, the assertion is what you want. So you want your sequence xn, any sequence, to be equidistributed along primes. So that's the statement. And now what you need to look at is what I need. So basically I need to understand my sequence along arithmetic progressions of size d. That's type 1. And this expression you already saw before, the d1, d2, before it was pq, but here this is the bilinear expression. But it's very different from what we saw before, even the type 2 sums, right? For two reasons. Crucial reasons. First is that you need to have a logarithmic gain on the right. So you see there is a log 22. This can be improved, but you need at least 2 logs at the very least, maybe 2 plus epsilon. In fact, maybe you need more, but yeah, 2 at the very minimum. So that's the first thing. And the other thing, so, you have rates. The other thing is that, yeah, if you look at the levels, so where are the D1 and D2? They can go all the way up to, n to 1/3, right? So before, if you think about Mobius, the idea, the success was in the fact that I'm allowed to fix P and Q, and then I'm going to let my n go to infinity, but P and Q are fixed, and I don't need rates. And ergodic theory loves this type of questions. I mean, this is where it enters. So there's no rates and the progression is fixed, say. Here, you can't use ergodic theory for 2 reasons. First, you have rates on the right, which ergodic theory never gives you. Just, I mean, abstract ergodic theory, if you don't do anything else. And second, also your transformation. So the D1, right, it changes with n. So it's not like you're fixing the step and then letting n to infinity, you are actually changing the step with n. So basically you are changing your transformation along with the length of the orbit. And this ergodic theory can't deal with. Yeah, so this is basically what I said here. So you need to control it quantitatively, right? And this is not an ergodic theory question. Therefore, that's the reason why the results on primes are much less than the results on Mobius. Yeah, we did. Okay, so this is a joint work with Giovanni Forni and Max Radziwiłł. So we studied semi-primes, so products of two primes, and it turns out that you can do a much weaker, you can have a much weaker criterion if you relax primes to semi-primes, so two prime factors. And it's weaker in two sense. Okay, you have still a log, but only 3. And then but the main part is that the D1, D2 are of size n to power epsilon, where epsilon is, it might be 1 over a million. Before here, the epsilon was like 1/3. So 1/3 minus something, but almost up to 1/3. Here it's just any epsilon. Yeah, and this allowed us to show, for example, that the horocycle flow, which I briefly defined here, but I don't think I'll have time because I want to move to squares maybe in the last 4 minutes. But yeah, the horocycle flow is equidistributed at 2 primes. And for this, we used some results on HT cross HT. So basically, the n to the epsilon, along with recent breakthrough by Lindenstrauss Mohammadi Wang, allowed us to enter the semi-primes. Okay, and one last thing I want to mention. The last thing I want to mention is polynomial averages. So now think about n squared. Okay, so we had 3 different settings. I hope I'm not confusing you too much. There was Mobius, where multiplicativity of the function was the key player. There were primes, where sieve methods in the form of type 1 and type 2 sums were the key player. And now we have polynomials, where we'll see what the player is. So yeah, let me give you some examples. So if you take an irrational rotation, then for every x, the polynomial averages, and for every polynomial they exist. It follows from van der Korput. So basically this. I will mention what's behind it. And then there is just another example. So for polynomial averages, it's really not much is known. These 2 examples are basically everything that's known. And the main player, so for multiplicative, it was multiplicativity. For primes, it was sieve methods. The main player here is this. So if you have a sequence, well, xn, I should say, just to be consistent, this is a criterion on equidistribution for a sequence xn, say. So xn, let's stick to an, but it has nothing to do with the weights. So if you want to understand an, then again, you see there is something like a type 2 sum, right? an plus h. Basically, you need to understand averages of an times an plus h, which generally, so if you write it in dynamical terms, ftpn is your an, so that's the sequence you want to understand. And then the term you get if you just use van der Korput is something like this. And this looks more scary, I want to say, right? I mean, that's what I wrote here. So if your system has no extra structure, if you write it like this, you see immediately that your problem is more complicated than the problem you started with, because I mean, now you have your old problem, which is here, ftpn of x, and you've added another term, which is also a polynomial term. So instead of having, just 1, you have now 2. Generally, it's much more difficult to study. That's the reason why these 2 are the only ones. So if you look at the rotations and nil translations, whatever they are, you can think about rotations only. These are the only ones that are accessible for squares or polynomials. And the reason is here, right? So if you take, so this is the key formula that allows to access rotations and maybe generalize to nil translations, is that if you take, so I'm just writing this expression for f being just a character e to the 2 pi I, and x being an irrational rotation, then somehow magically what happens is that the n squared is killed because it's a character, so you can put it together, and you're left, so you are summing over n, you're left with a linear phase, right? So for rotations, magic happens, and you started with a problem that had quadratic complexity, and somehow you reduce it to linear complexity, right? But this is because you have a very robust structure of functions, right, for rotations. I mean, you have characters that basically, you know, if you multiply two characters, it's still a character. Generally, I mean, we can't expect that for a general dynamical system, multiplying two functions is going to give us a nicer function, right? I mean, generally, it's much worse. Yeah, and therefore, I mean, you see, the point is there are many questions that you can ask here. One of them is just to show you where we are in this setting is the point is that whenever you can apply van der Korput, so this kind of reduction once, you can apply it many times. So basically, we don't know of a system which would distribute along squares, but not along cubes. Because if you can do, so distribution along squares means you can do it once, but whenever you can do it once, you can do it many times in all the examples, and then you can get to cubes, right? So just by iterating this. So if I started with n cubed, if I did it once, I would get to n squared, but I can do it again and I get to n, right? So, and the same with n to any power. Yeah, so the new method that kind of, maybe this is the last slide I wanted to mention, is that we would like to drop the van der Korput approach, because as I said, for most systems, essentially all except rotations, you make your life harder. So what we try to do is we try to input more dynamical point of view. Yeah, so notice that if I take a prime number, then I know how it behaves in arithmetic progressions and residue classes, right? So I know that primes that are 1 mod 3, there is about the same as primes that are 2 mod 3, right? So basically, if I have a rotation on 5 points, then I know that the prime number theorem holds because I have primes that are 1 mod 5 are the same as prime, and so on. So we defined the notion of rigid. I mean, it's not we defined, sorry. A system is rigid if along identity it behaves like a periodic system, okay? Of course, it's not equal, but it just converges. And there are a typical dynamical system is rigid. And then what we wanted to use and what we are using is the fact that, you know, along these NKs, your system behaves like a rotation, like a periodic system. It's very close to a periodic one. So you can approximate primes, the orbit along primes, just by arithmetic progressions. And using a variant of this, we are able to show that with Max, the orbit of horocycle flow are dense along the sequence n2 minus delta. So we couldn't do n squared. That's still open. But before that, I think Venkatesh did n to 13/12. I think that was the kind of limit, 1 plus 1 over 12. So we can do 1 plus anything less than 1, right? So, and a young student from Krakow recently showed that who I'm working with as well. He recently showed that there are weakly mixing systems which equidistribute along squares. And this is an interesting result because weakly mixing, so I didn't define it and I don't want to, but weakly mixing essentially means that you don't have functions. It's a precise way of saying that you don't have functions that behave like this. It's like the opposite extreme of having eigenfunctions and characters. So, you know, this result indicates that some new method had to be used, and very roughly, I mean, this is rigidity was kind of the main player. Yeah, I think that's it. Thank you for listening. Yeah.
Thank you, Adam, for this very nice lecture. Are there any questions, maybe, for Adam?
Maybe can I stop sharing, you think? Yeah.
Oh, yes. You can stop sharing. Well, I wanted to ask about possible applications. Since dynamical systems are quite applicable, you mentioned that Liouville function, Mobius function. do you work with somebody who deals with something which is applied, maybe in physics or something like that? I know that Mobius function has some applications in physics, but I can't remember now.
So I think, to be honest, I think so. We this, I would say, this roughly really so I didn't want to mention that, but I probably now should, right? So in physics, classical ergodic averages are what you study. So I won't probably go all the way because, you know, you do your experiment and you sample it every hour, right? There is no reason for sampling it along squares, for example. So I think this part of my research, so we have some results I work, but also, but it's not related to that, on applications to physics and statistical behavior of systems. But this one is more really about, you know, interactions with number theory. So the fact that your sequence is sparse, I don't think it, you know, it allows you maybe to prove some results in number theory, maybe applied number theory, but yeah.
I understand. So it has a great impact for number theory and results there.
Yeah, it's rather that, yeah. Yeah.
Oh, we have one question from Andre. I'm not sure. I don't know how to read it. How to open chat? Christina, do you know how to?
Well, if Andre wants to unmute him or herself, then maybe you can post the question. Yeah. Okay. Nice.
Thanks. So it's just a very general question. At the start, you mentioned also probability theory and that you partly work in it, I think. Is there any connection of what you did, direct connection, to anything here? Any part of randomness?
Okay, so I think there are, well, at least I think two things that I work on, which are, I would say, vastly orthogonal in a large sense. So one is I study statistical behavior of dynamical systems. So for example, you take so this was probably the initial motivation of Lawrence, who was studying temperature and prediction of weather, right? So basically there you try to say to what extent a system that is a model for a physical system can behave like a sequence of independent coin tosses. And this I work on, but I mean, I don't think this is related to what I was discussing today. So I think these two are, I wouldn't say maybe orthogonal is maybe too strong of a word, because some methods overlap. But the fact, you know, it's really, I think combinatorics and number theory is really the connections to on the dynamical side to what to what I presented. Yeah, I was thinking if I should talk about physical applications or number theory, but I thought maybe for a broader audience, you know, like it's easier to understand maybe what a prime is than like what central limit theory. I don't know. Yeah, I don't know. It was, yeah.
And the lab here is Lebesgue.
Yeah, the lab denotes the Lebesgue measure on the cycle.
Okay.
Yeah.
Okay. Thank you. Thanks. Thank you.
Thank you. Are there maybe some other questions?
Can I ask a small question? So you were talking at the, I guess it was at the beginning, about the sparse ergodic theorem. What does sparse mean?
So sparse just means that the sequence along which I'm going to sample the orbit has density 0. So for example, primes, right? If I look at the interval from 0 to n, there is about n over log n primes. So it's much less than n, which is the total window. So sparse in that setting means I'm sampling along a sequence whose asymptotic density, say upper Banach or whatever density is 0. Yeah.
Okay, thank you.
Any other questions, maybe? If not, then Adam, thank you for accepting our invitation and thank you for giving this very nice talk.
All right,
Hope
thanks.
to see you again.
Yeah, maybe I'll
Yeah.
come to to the next series, which is a month from now, right? Yeah.
Yes.
Yeah.
All right.
Thank you very much.
Thank you
All
very
right.
much, Adam.
All right. See you. Bye bye.
See you.
See you.
Bye.